Hello and welcome. In this video we are solving twosome. Basically, you're given an array with numbers and a target number. The goal is to find two numbers in the array which add up to the target, just like in this image. To understand the problem better, let's move on to an example. Let's say that we have this array and we would like to find two numbers which add up to 9. A very natural strategy that we can apply is to generate each pair of numbers and check the sum against the target. To make it easy to visualize, we are going to use this table to record the sums of any pair of numbers. And as you can see, the first column and the first row are simply made up of the same elements in the array. Let's start with the first element, which is -1. It can form a pair with 8. Adding them together, we get 7. But 7 is not equal to the target, so we can move forward. Next we try -1 and 4, which add up to 3, and 3 is not equal to the target, so we can move forward. This time we try -1 and 7, which add to 6, and 6 is not equal to the target, so we need to move forward. We try -1 with 2, which add up to 1, and 1 is not equal to the target, so we can move forward. The next element we can check is 9, and adding it with -1 we get 8, which is not equal to the target. Next we try -1 with 5, which add up to 4, and 4 is not equal to the target. We have checked all the pairs which have -1 as the first element, and we did not find the target. So we can check the pairs of numbers which have 8 as the first element. I'm going to let the animation run since the logic is very simple, but feel free to pause the video and check if you get the same results. Now we have found a pair of numbers which add up to the target, and we can return 4 and 5 as an answer. But an important thing to notice is that the solution may not be unique, as 7 and 2 is also a valid pair. But the problem statement neither gives us a constraint on the pairs nor asks us to find all of them, so we don't need to do more work. Before we move on to the code, I would like to bring to your attention something that we're going to need in order to determine the time complexity of this strategy. And it is that we need to know how many comparisons we actually had to do. And it's quite simple. If I highlight the pair that we have checked, you can count them and see that we made 18 comparisons. You may be able to see it, but out of those comparisons, some of them are actually needless. And in order to spot them more easily, here's the trick that we can use. If we are adding two numbers x and y together, then x plus y gives the same result as y plus x, just like 1 plus 2 gives the same result as 2 plus 1. And with that observation, we can actually see that we did not need to check the orange part in the table. And we can actually extend this observation to the entire lower triangular part of the table. If we remove them, then we can see that the only comparison that we really needed to do are in the blue region. And as you can see, it reduces the number of comparisons from 18 to 15. So we have already made some improvement in our strategy, and we can actually go further and estimate the maximum number of comparisons that we could expect. And it's fairly easy, we just need to count the number of cells in the blue region. Counting them, we get 6 plus 5 plus 4 plus 3 plus 2 plus 1, which add up to 21. In the general case of an array with n elements, we could expect the number of comparisons to be 1 plus 2 plus 3 plus 4, etc. all the way to n minus 1. And we actually have an expression for this sum, which is n times n minus 1 divided by 2. so we can expect the time complexity to be n squared. This is the Python code for this strategy that you can find on my GitLab, and you have the link in the description. As you can see, we are generating only the pairs of numbers in the upper triangular part, and if we find a pair which add up to the target, then we early stop and return it as an answer. And note that in the end, if we did not find a pair which add up to the target, then we return -1. As mentioned before, the time complexity is bigger of n squared, and for the space complexity it's bigger of 1 because we're not creating some extra memory. Now this solution is okay, but it's actually not the best. The time complexity is too big, so we need to do something to improve the solution. And to see how we can do that, we can notice that if we are looking for x plus y to sum to some target t, then what we can do is to check for each possible value for x if there exists a number y such that y is t minus x. And we are going to look for y in the values that we have already visited. So if we want to be able to take a look at the values that we have already visited, we need some sort of data structure to do that. And ideally, this data structure should have constant time for insertion and lookup. And there are two candidates for this data structure, either a hash map or a hash set. Now let's see this strategy with an example. We start with an empty memory. First we check x equals -1, and the number that we would need to add it to in order to get 9 is 10. Now, have we seen 10 before? No, we have not, so there's nothing that we can do for now. But before we move on to the next element, we add -1 in the memory because we have just visited it. Next we move to 8, and to get 9 we would need 1. But we have not hit 1 before, so we have to check another value for x, and before we move to the next one, we add 8 in the memory because we have just visited it. For the next step, I'm going to let the animation work. We have found the pair 2, 7 to be a solution, but again that is not the only one, and if we continued with this strategy, we would also get 5 and 4 to be a valid solution. But it's actually beyond the scope of the question because we are only asked to find one solution but not all the solutions. Before we move on to the code, we can compute the number of lookups and insertion. Here we have 5 lookups and 4 insertions in the memory. But in the general case, we would expect their sum to be smaller than twice the length of the input array. Let's look at the code. Here I have chosen to use a hash set for the memory, so it doesn't really change anything. You could also use a hash map and you would get the same result. For each number x in the array, we look if target minus x is in the memory. If so, then we have found a solution. Otherwise, we add x to the memory since we have just visited. In the end, if we have not found a pair, then we return -1, just like before. Based on the observation that we've made for the number of lookups and insertion in the memory, we can expect the time complexity to be a big of n. For the space complexity, we know that we are now explicitly using memory to store the numbers that we have already visited, and at most we would have n numbers in memory, so the space complexity is a big of n as well. That's it for the two-sum problem. I hope this was helpful and clear. If you have any question, feel free to post in the comment. Don't forget to like and subscribe for more videos, and I will catch you in the next time.